Alright, this is the 4th quiz I'm recording. A little bit sick of taking these quizzes. Whatever. If it helps you guys, it's worth it. So, hopefully you guys remember this quiz. It wasn't too long ago. Your memory is probably better than mine. So there's a box, or a block, on this ramp. We're not given the angle, but we are given that if the block goes along the incline by 5 meters, it gains a height of 1 meter. So if it goes another 5 meters, its height is 2 meters, and so on. So we can find the angle just by looking at these triangles. Either you have a hypotenuse of 5 and an opposite side of 1, or or a hypotenuse of 10 and an opposite side of 2. Either way, you'll probably suspect that the sine of the angle is the thing to use, because that's either 1 over 5 or 2 over 10, and those are the same. So the angle is the inverse sine. Let me shrink that back. Get my calculator out. 1 divided by 5, inverse sine. 11.537 degrees. And now we want to calculate the force F, the work done by the force F for each 5 meters that the block goes along the incline. So the displacement is 5 meters this way. 5 meters, there's got to be some unit vector to make this a vector, but I'm going to leave that off for the moment. And then there's a force F, and that's just the magnitude 300, or whoops, I shouldn't have vector sign there. So that's 300 in the I hat or x direction. So actually, you know what? I'm just going to write magnitude of the displacement vector s is 5 for the moment. And this represents the vector of the displacement. Now, the work done by this applied force F is going to be, since F is a constant, it's going to be F dot S. Alright, so this is true no matter what. But how do we write the vector F? Well, we could do it this way, and that would correspond to using the normal x and y coordinates that we're used to, or we could use a rotated coordinate system, and to differentiate x and y here, I'll put just primes here. So the primes mean the rotated coordinate system, and Oh, I don't know. In black, I'll put the shadow of the old coordinate system here. And then here I'll do the shadow of the rotated coordinate system. Ah. That looks too much like a G. So, in light blue, I'll change the color of the applied force. So, that's supposed to have the same magnitude as this one and this one. I'm not good at drawing, so these light blue vectors are all the same. They're F. In the normal coordinate system that we're used to, that vector is just the magnitude times I hat, like I wrote up here. Like I wrote here. But in the rotated coordinate system, that vector is known by a different name, or we have to write it differently. It's still the same vector, but now the x component is this arrow, and then the y component is this arrow. So I've got these two new components. Here's the right angle. And that doesn't look like it. That should have been theta, same theta as the incline. Because if theta was 0, all these coordinate axes would coincide. X prime would point in the same direction as x. And then I want to incline the rotated coordinate system by the same angle as the incline. So that's what that means. And that's why that's a theta here. And so like all these solid lines in the rotated axes, the solid lines, come off the dotted lines by the same degree. So all those are thetas. And so this component of the applied force is F cosine theta, and I'll have to differentiate it, the I hat. So I'll put a prime, and then the y component of F, we have negative F sine theta j hat. The in pink, so the displacement vector S here, S. The displacement vector in the rotated coordinate system is easier. That vector is just 5 meters in the positive x prime direction, so I hat prime. In the unrotated coordinate system though, that displacement vector needs to be written in component form. So we have a 5 cosine theta I hat, no primes, plus 5 sine theta j hat. Alright, I've I've run out of room, but the work done by this applied force, so F dot S, in either coordinate system should come out to be the same. So let's bear with me for 1 second. I'm going to modify this quiz so I have a little bit more room. Okay. So the work that the applied force does is F dot S, so that's F I hat dotted into 5 cosine theta I hat plus 5 sine theta j hat, which is 5F cosine theta I hat dot I hat plus 5F sine theta I hat dot j hat, which is 0 because those are orthogonal. We have 5, what was the magnitude? F is 300 cosine of 11.537. So I get 1,469.7 joules. So I expect F dot S to be the same over here. F cosine theta I prime minus F sine theta j hat prime dotted into 5 I hat prime. It's equal to 5F cosine theta I hat prime minus F or 5F sine theta j hat prime dot I hat prime. That's 0 because those are orthogonal. And then we have again 5 times 300 times cosine of 11.537 degrees, 1,469.7 joules. So, once again, calculating the work done by this applied force is just F dot S. Between these two coordinate systems, the vectors F and S were the same. It's just, how do I represent that? These are with the unit vectors in the unrotated coordinate system. And then the vectors here just represented in the rotated coordinate system. Right? F and S are the same. It's just, how do I represent F and S that are different? Alright, moving on. The ramp is made of rollers and can be considered frictionless. What is the maximum mass of the box that your force F can move up the ramp? Now, we didn't have to use the mass for so far, and the mass now is irrelevant. So, what does this mean? What does this mean? So, the key word here, and when I read this problem, I was scared that it would confuse a lot of students. And I think this part B, if you got part B, it's harder than other part Bs. Well, there's only one other part B. The other part B I think was a lot easier. And just, I probably linked it somewhere. So what is the maximum mass of the box that your force F can move up the ramp? So, just as it is, just like this, if I were to put the block on the ramp, and just leave it be. Gravity would act on it, and a normal force would act on it due to sitting on the ramp. It can't go up the ramp with just those two forces. I mean, just looking at this line, there is more forces to the left of that line than to the right. There's nothing on the right. So this block is going to tend to go leftwards and perhaps downwards or upwards, depending, well, downwards really, because N is a reaction force to a part of W. It's the horizontally applied force to the right that gets the block to move up the incline. But at the same time, when you're applying this force F, you're pushing on the box, you're squeezing the box, or I should say you're pushing the box into the ramp harder. And if you imagine a little bathroom scale, a tiny massless bathroom scale, and you put it between the box and the ramp, that extra force that you're applying on the box is squeezing the bathroom scale, is causing the bathroom scale to be squeezed even more. And bathroom scales measure normal forces. So if I put the bathroom scale between there, and then I put on this applied force, F, the normal force goes up, the weight stays the same. So I'm going to see a bigger reading on the bathroom scale. I kind of don't know where I was going with that. I think I was thinking about the other part B that had more to do with it. Anyway, you know what, when you don't know what to do, you just start writing things. Let's look at the total force. That's N plus F plus W. And in the rotated coordinate system, W can be written as the vector W can be written as let's see. I need to find one of these. So if this is theta, then this is theta, which means this is theta. Okay. So in the x prime direction, we have negative magnitude W times sine of theta I hat prime. And in the y direction, W cosine theta j hat prime. N, written in the rotated coordinate system, is, since it's pointed along there, that's just the magnitude of N j hat prime. And then F in the rotated coordinate system we found up here. It's F cosine theta I hat prime minus F sine theta j hat prime. And this is equal to ma, or max prime I hat prime direction, plus ma y prime, the y prime direction, or j hat. Now, it's this component that we're interested in. That is f total in the x prime direction. If that is a positive number, then the block accelerates in the x prime direction, or up the incline. If this is negative, then it accelerates in the negative x prime direction. When it's 0 is when the box it doesn't accelerate, but it can either go up or down. The forces in that direction are in equilibrium, they're balanced. So the plan now is to add up all these forces, like I'm doing, but using the component form in the rotated coordinate system. Examine the x prime component, and then we'll see what happens. So f total is, let's add up the x components. Let's do this one first, since it's positive. F cosine theta, and then we'll add this, negative sine theta I hat prime. We'll do this one, n plus that component, so n minus cosine theta, plus this component, so minus f sine theta j hat prime. And again, this is the x prime component of the total force. If that's greater than 0, the block accelerates up the incline. If it's negative, the block accelerates down the incline. If it's 0, it can either go up or down. And it depends on, if f is set and theta is set, then it depends on what the mass is, because that's mg. So when f cosine theta minus w sine theta is 0, is when we have 0 acceleration traveling along the incline. So f cosine theta, if f sine theta divided by f cosine theta divided by sine theta is w, or mg, then, well, divided by g, so if m is equal to f over g times 1 over tangent theta, or I could have called that cotangent theta. That's the critical mass. If the mass is greater than this, let's just get this number first. (300) divided by 9.8 divided by 11.537 tangent equals 149.97, so 150 kilograms is the mass with the right sig figs. So if m was greater than 150 kilograms, then this term would be bigger than this term, which would make the overall x prime component of the total force negative. And if that were negative, then the box would not be able to go up the incline. It would slide down the incline. It would accelerate down the incline. And then if m were less than 150, then this would be smaller than this, which would mean the whole term here is positive, which means that the x prime component of the total force is positive, which means there's a positive force pushing the block up the incline. So it's going to accelerate up the incline. The maximum mass for the box have is about 150 kilograms. I mean, to 3 sig figs, it's 150. So there you go.